Hello, I'm Tad Dallas, an assistant professor in biological sciences at University of South Carolina. This talk is based on some work presented at the Ecological Society of America conference in 2022. There's a short talk around an organized session that's centered on the possibility of predicting networks of ecological interactions across spatial and environmental gradients. And so when I was invited to the talk or to give a talk, I thought this is going to be really challenging. And so I set up the sort of problem and the title sort of before I actually did a lot of the actual simulation work that I'll present here. And so I decided to call it the cold black abyss of network prediction in space, thinking this is going to be hard, I'm going to fail. Because it is a really hard problem. And so predicting networks and interactions among species, between species in general, is an incredibly tough challenge. And it's something that has sort of driven some of my research for the past 8 years or so. And that was really focused on only predicting the interactions between species. And here, this challenge was predicting the entire network of interactions. So not single interactions, but sort of complex web of interactions among species. And so there have been many great approaches at basically this problem. And so Saravia recently had this really neat model in which they took the meta web, this entire, what interactions have we ever seen? And we compile that all together, agnostic to things like geographic space, range overlap, for the most part, et cetera. And it's all about downscaling from that meta web to these local species webs. And that's what I'm going to focus on here, is if we have knowledge of the global web, what can we say about local interaction networks in given geographic locations? And so the overarching question is, how do we predict interaction networks? And specifically, I'll focus on host parasite networks. A lot of this, though, is fairly limited in terms, and one of the common limitations that we sort of hit when we start to address these problems is the problem of data. A lot of the times we simply just don't have the data to assess it. So the data that I'm using for this is this really great global data set from the London Natural History Museum. It is only on helminth parasites, so those are worm parasites, contains right around 250,000 host helminth association records. So this parasite or this helminth species infected this host, and it's fairly decently globally representative. The one downside of that would be that it's currently only georeferenced to geopolitical locality, which is not ideal. And some work in my lab, we're currently trying to get funding to basically geo-reference a lot of this to a finer scale. That can be a really great data resource for researchers to sort of delve into. And the size of these data are like, it's always like a nice slide to show because I think it's really neat. And so this is, every point here is an existing database of host parasite records. And on the x-axis, we have the number of unique host species. On the y-axis, we have the number of unique parasite species in that record. Everything's on log scale. Point size is proportional to the number of records in the database. And we see in that top right corner is this data that I'm using. These data are fantastic. Can't sort of plug them more. Really great resource, both in terms of diversity of hosts and parasites, as well as overall number of records. Ooh, there we go. And so now that we have the data, we can start thinking about the actual prediction of these local networks, where I define local network here as the network in a given geopolitical location. Can we use information about this global interaction network to predict and downscale to these local interaction networks? But it's important to note that other people, like other folks, have thought very, very deeply about this problem. So if you haven't seen this review, which many of you I imagine haven't, feel like reach out to me if you need a copy. Really great paper, citation down below, basically set up the problem, different approaches, really like sort of reviewed the landscape of the issue. And so while others have thought really deeply about this, I'm going to start by thinking incredibly shallowly. So I'm going to make a bunch of assumptions and try to develop from an absolute baseline up to maybe a slightly more informed, but still quite sort of shallow thinking, naive baseline, just to see if we can do it, to see the sort of complexity of the problem, see how hard it is. And so I'm going to make this assumption where basically any interaction that is in the global network between two interacting species will be present whenever that host and that parasite species in the global network that interact are present. So this ignores so many things, so many things. But it's still very, very interesting. And it's like, it's a good baseline assumption to make. And so basically I filled in all of these links in all of these local networks. And so here in this left plot, every point represents one of those geopolitical locations. And so on the x-axis, we have the true connectance being the fraction of realized links in the network. And on the y-axis, we have that, what I'm calling simulated connectance, which is basically like when we fill in all of those interactions from the meta web, like how many interactions, what fraction of interactions do we get? So it's important to note that nothing is going to fall on the lower right of this plot, right? So those points that are directly on that one-to-one line means that the global web was able to recapitulate all of the interactions observed for that given location. And we see like it's generally a pretty positive relationship, which is actually sort of like heartening. And you see some aberrant points where the true connectance is much lower than the simulated connectance. If you can see my cursor, I'm not sure if you can, but that point right around like 0.37 or so on the true connectance. But this is an obvious like sort of flaw, is that connectance really isn't the end all be all of things. And we'll revisit that later. And this is it's very much an ongoing project. There we go. And so that did halfway decent. Like that approach provided a good like baseline with which you can layer on complexity of this. You can layer on things like geographic range overlap, how often things are observed interacting, given that like species can be really widespread, species can be very sort of endemic or linearly spread. There's the influence of islands and very like disjunct populations and things like that. So let's build on a little bit more complexity. And I'm going to say the probability that two species will interact is determined by the number of times we've observed them to interact. So therefore, this sort of biases it toward species that are very, very widespread. Really common species would tend to be observed more. And also we just have to acknowledge that there's an inherent sampling bias in terms of the records that go into these databases, right? And so like charismatic species, like charismatic mammals or things that are easy to sample, will probably have more records and will probably have a better defined host or parasite community. So it's important to know. And so I'll show basically a similar plot to last time in which I build these networks up probabilistically. This time, I'm sort of stochastically building the network up until it reaches a certain value of connectance. And if you're starting to already think like, oh, wait, there's some circularity there, you're absolutely right. I'm digging into that currently. And so the circularity is that if I stop when I hit the simulated connectance that matches the true connectance, what does a plot like this really mean? Right, so I've filled in some of the interactions probabilistically. I observe connectance that looks just like connectance in the true network, but that doesn't matter. And so that's an important takeaway from this, is this plot is completely like sort of artifactual because we don't really care about connectance. We care more about better descriptors of network structure. So things like nestedness and modularity, degree distribution. And then maybe like more true to the fact is we actually care about what species we're good at predicting and what species we're bad at predicting, or what geographic locations we're good at predicting and which ones we're bad at predicting. And so take this more with a massive grain of salt and know that this is sort of just ongoing work that we're sort of just digging into. And so that was my thinking about it very shallowly. When I'm going to also plug this paper again, others have thought about this problem very deeply. And so this is sort of where I guess we are as a lab group right now. We're sort of chasing the world in terms of the prediction of interaction along spatial and environmental gradients. I will update this talk whenever the project gets pushed forward, which I think there's simulations running right now. And there's a lot of exciting work sort of going on like within this realm. And so there's updates to follow. But it is important to note, as I mentioned earlier, that so much of this link prediction and trying to recapitulate the local network from the global network of interactions sort of buries the lead or sort of ignores that these widespread species are going to differ in their ability to be predicted relative to narrowly ranged species. Island communities may be difficult to predict if they're really disjunct or really removed from the mainland. So you can start to apply some theory of island biogeography. You can start to apply some distance-based weighting, right? And so sites, if you're trying to predict the local web in a given site, you probably want to upweight interactions that occur more locally, like more nearby than those that are really far away. To my knowledge, that hasn't been done before, and I think that would be a really nice feature. And exploring these differences is really important, both to the prediction of individual interactions as well as the prediction of those entire local networks. And I think the importance of some of the sort of very brief analysis that I've done in this realm to make this talk is that baseline predictions are really, really useful, because even if you just ignore like the approach that I took and you mash in species traits and you mash in geographic distance and you mash in environmental gradients, comparing performance to those baselines just offers a nice comparison, because you can say, oh yeah, look, traits did much better than this really uninformed, silly baseline that Tad put forward. And so I think in this field, as we push forward, we need to ask ourselves a lot of questions. The most important I highlighted in orange, which I sort of alluded to, and it's just how can we build models that then compare against a better, sort of the informed baseline that I put forward. So how can we stand on the shoulder of some giants? How can we build up from here, from this very simple place where we are currently, to maybe modeling spatial environmental gradients explicitly, maybe considering distance-based weighting, maybe, who knows, joint species distribution models, hierarchical models, who knows? There's just a lot of really exciting sort of frontiers within this space. And so with that, it's really not the sort of cold black abyss as I was pitching it to be in the talk title. Rather, I'll sort of rename the talk the exciting and developing future of network prediction in space. And so thank you for listening. My lab website is at the bottom of this, and please reach out if you're interested in some of these things. And with that, I will end the call. Nice, take care.